There is another way of doing a two-sample confidence interval, okay? Or doing a confidence interval if you have two samples. So come on back to my screen if you haven't already. We're going to take a look at that and how that works, okay? So another way to compare two means from two different samples is if you can somehow pair the data. All right, if you have paired data, then you can do this procedure. All right, so think of this like data that comes from a matched pairs experiment. If you remember, we'll talk more about that in a bit. If you don't exactly remember what matched pairs was, it doesn't have to be an experiment. It could be an observational study, but your observational study would still have pairs of individuals that you could, pair together. So a matched pairs experiment or paired data can be done in two different ways. Okay? This hopefully will jog your memory a little bit. So each individual does both things in a random order. Okay? So say I want to see if listening to music while taking a test is beneficial. Okay? Is that the case? So I get my random sample of people, and they all take the test, or take two tests, and they do both. So they would take a test listening to music, and they would take a test not listening to music. Now they would do this in random order. That's my randomization there. So some people would listen to music first, and some people would not listen to music first, and then they would all switch. But each person does both treatments or both options. Okay, that's one way to pair data. Each person now has two data points that are paired together. Or you can pair treatments to similar individuals. So I could take the highest level or the highest grade in the class and the second highest grade in the class, pair them together, and then randomly assign music, non-music. Then I take the next two highest grades. They're similar. And then randomly assign music, non-music. Okay? I'm hoping that kind of thing sounds familiar. We talked about matched pairs before. Those would be scenarios where we would have data that is paired together. All right? So the basic idea of what we're going to do here is you combine the data. So you take the two data sets and you turn them into one data set by subtracting the data pairs. So you take each data point with its pair and you subtract them. This now gives you one sample. All right, because you subtract them, and the result gives you one data sample to do a confidence interval on. Well, because we took the two samples and combined them into one, well, now we just do a one sample t-interval. That's the kind of weird thing. So yeah, we had two samples, but because we turned them into one by subtracting the individuals, now we have a single sample that we do a one sample t-interval. So the process here is going to be the same. We just have to recognize, oh, we are taking the two samples and turning them into one. Then the process is the same as always. So I don't want to write out all of this. I just grabbed the example from the book, and we're going to look through their answer and highlight a few and write down just a few key differences, because the process is almost exactly the same. Okay? So, which twin is smarter? You guys know that the identical twins are like gold mines for human experiments and such, because they have the same DNA, and so you can do a lot of things like, hey, how does the humans react? Because now you have your control and experiment and everything. I mean, you have to do it humanely, of course. And even this one, this is where they have two identical twins that were separated at birth. Is what this one is. Talk about a small sample size. Identical twins that were separated at birth. So, construct and interpret a 95% confidence interval for the true mean differences in IQ scores. All right, the true mean differences in IQ scores. So here we have two data sets. We have an IQ score for the twins that were in high income households. And we have an IQ score for the twins that were in low income households. And so you see we have a data set here for these. And then we have a data set here, our second sample, for the high income. But we're not going to do a 2-sample t-interval, because what they did is they combined them. They subtracted each similar, or twin minus twin, I guess you could say, and turned this into a single data set. All right? And so we're no longer going to do a 2-sample t-interval. We're going to do a 1-sample t-interval on this difference. So once we have that identified, this is going to be the same as pretty much everything else. Okay? So the state, we're going to do a 95% confidence interval. Oh, here's a slight difference. They called it the mean, the mu, and then DIFF for difference in the bottom. Okay? But whatever letter you use, you still have to identify what that letter means. The true mean difference, high minus low, in IQ scores for pairs of identical twins raised in separate households. Nothing different there, right? Besides that this is a difference. All right, now here's an important part. We are doing a 1-sample t-interval. Again, because we combined the 2 samples into 1 sample, we now do a 1-sample t-interval. So that's one slight difference there. Okay, it might seem a little weird. But now the conditions we have are the same. Random condition. Did we take a random sample? And I think the problem did say that yes, we took a random sample of 12 pairs. So each sample, of course, does have to be random, right? All right, 10% condition, that's the same as always. Assume that 12 is less than 10% of all pairs of identical twins. Same as always. All right, so our normal/large sample. This is our large counts condition. So we're not greater than 30, right? 12 is not greater than 30. So that would be an issue. But they graphed our sample. Now that might be worth saying. Do you see which one they graphed? I want to type something. Let me type something. Well, let me type over here. So if I type over here, can I drag it over? Yeah, I can. All right. So you might make a note. We only graph the combination of the 2 samples. And that's the one you look at. Hey, is it roughly symmetrical? Does it have a huge amount of skew? Does it have major outliers? All right, but they graphed the difference. Graph the difference. All right, none of that, I hope that not too much of that is different. Any questions on that first part? Anything there not make a whole lot of sense? All right, again, feel free to throw something in the chat if you think of something that doesn't make sense. Well, now that we're allowed to do this, we're going to do the one sample t-interval. Now, there's many ways to do this. The book shows its work all the time. Now, I will say, you do need to be able to recognize all the parts of a confidence interval, okay? No, we don't really do this by hand very often, but you do need to recognize where this formula comes from and all the parts. Because on a multiple choice test, this could be an answer choice right here. So make sure that you can recognize how to get the t-star and the standard error formula. Make sure you recognize all of those pieces. Now, if it's not a multiple choice, you of course can just run it through your calculator and get the interval. But again, this is a one sample t-interval. All right, they don't make that super clear here. I'll write that over here on the side. This is a one sample t-interval. They would have used degrees of, they show it there, degrees of freedom 11. All right, because the combination has 11 data pieces. Okay, where is it? Right here in this color. This one right here, this is what we are doing our confidence interval on. It has 12 data pieces in it. And that's the confidence interval we are doing it for. So they do have the mean and the standard deviation right here. And so that's what they were using. So x bar is equal to 5.883, or 833, sorry. And the standard deviation of the difference is equal to 3.93. Now again, that either has to be given to you or you got to type it into your calculator to figure it out. And the video will again remind you about that. The sentence is then completely the same. Just make sure you have your context in order. Captures the true mean difference in IQ scores among pairs of identical twins, etc., etc. Now, I think the big idea here, or the complicated thing, is realizing when this is happening. So if I go back to our Desmos here for just a second, we do need to realize that that process is not possible in this scenario. Okay? We don't have pairs in this scenario. We have the brand name Samsung and the generic ones. There's no pairing these batteries together at all. And each battery is not doing two tests or anything like that. Each battery is not doing two tests. So this is not, you do need to realize the one you did on the Desmos is not a paired test. It's not a paired data set. And so you have to do what you did. 2 sample t interval. But sometimes the data is paired together. And if there is some kind of pairing and you can subtract the data, then you can turn it into a 1 sample. Okay? Questions? Anything there seem crazy, weird, or unclear? All right. Hopefully, yeah, that's not a huge stretch. I did want to share here, I got 5 minutes left. What if we didn't pair the data in this scenario? All right, what good does this do us? If you might remember from way back in the day when we did a matched pairs experiment and we looked at that, the matched pairs reduces variability oftentimes, right? It makes your results more accurate. So if we did that in this case, okay, I just did it for the fun of it. So here's the dot plot for twin A's IQ and twin B's IQ scores. They're not a whole lot different, are they? They really aren't that different. We don't see that, hey, this person, where am I? Might be connected to that dot. This person might be connected to that dot. And that the overall trend is an increase, okay? If we don't pair them together like that, well, then we don't, maybe something like this is happening. Maybe, yes, some of them are going up like that, but maybe some of them are coming back this way too. Maybe they're paired like this. We wouldn't know. And so when we run a 2 sample t interval, all right, I found the x bar of A and the standard deviation of A, and then the x bar of B and the standard deviation of B, and you get a confidence interval of -1 to 13.5 for the difference in their IQ scores. Well, the important thing there is what number is in that interval? 0. 0 is a plausible difference in their IQ scores in this case, which means 0 means no difference, right? So a plausible answer is that there is no difference in their IQ scores because 0 is in the interval. It's just as plausible as any of the others. Whereas when we paired them up, take a look at this answer. 3.3 to 8.3. See, that's a much narrower interval. It's much narrower. And 0 is not in the interval. So we do have convincing evidence that the twin from the higher income had a higher IQ than the twin with the lower income. Wow, that did not work very well for highlighting. Nice. But the confidence interval is much narrower. It gives us much better information. There's much less variability when we can pair them together. So that's one of the benefits of this, actually. All right. So your homework will have some questions like that on it. Hopefully they make some sense. But beware, it does have a few like the ones from the Desmos, I think. I tried to put both on there. So it will have some that end up being 2 samples. And then it will have some where it's paired together and it ends up being a 1 sample. Let's try to put those together. A reminder, your video lesson, you're not watching the whole thing. Just listen to the intro and then skip to your calculator section. That's all you need to watch, okay? And quiz next time. Quiz next time. All right, that's it for me, ladies and gentlemen. Have yourselves a great, great day. Come on by office hours if you need anything, and I will help you out. Bye, everybody. See ya, see ya.